Okay, so hello. Okay. Anyway, so it's a great pleasure to introduce Vera Fischer for today's talk at the virtual set theory seminar, and she is going to talk about independent families, spectra, and indestructibility. Okay, go ahead, Vera.
Thank you. Thank you for the introduction. Thank you for having me and for the invitation to speak. So I will talk about independent families, and I want to consider three main aspects of independence, of such independent families. I would like to talk about maximality and natural strengthenings of the notion of maximality, which would be very useful in terms of forcing combinatorics. Very closely related is the notion of being indestructible by various partial orders. And finally, we will be looking at the possible cardinalities of maximal independent families, with other words, at the spectra of such families. All right. So everyone should know, of course, what an independent family is, but nevertheless, I'm going to remind the definition. So we have a family of infinite subsets of the natural numbers with the property that any two non-empty finite disjoint subfamilies correspond to an infinite subset, to which we refer as a Boolean combination, namely the set which is obtained by intersecting the members of the first family with the complements of the members of the second family. All right, so such a family is said to be maximal if it is maximal under inclusion, and of particular interest is the minimal cardinality of such a family, the independence number. All right, so since I will be talking about such families for a bit, I want to introduce some notation. A very useful way to denote Boolean combinations is to look at functions from the family into 0, 1, and simply identify a Boolean combination with the intersection of the preimages of 0 with the complements of the preimages of 1. Okay, so then A superscript H would denote the associated Boolean combination, and for us, this would be a very useful, an object that you'll keep on looking at throughout the talk. Okay, so another terminology that's just a very abbreviation that is useful to have is that whenever we have two Boolean combinations associated to functions h prime and h, if h prime has a larger domain, this means that the associated Boolean combination is smaller. And we'll be saying that the Boolean combination H prime is a strengthening of AH. All right. So just to get a feeling of how these combinatorial sets reals work, let's go through the proof that such a countable independent family is not maximal. All right, well, so what we want to do is we have some countable independent family, and we want a set A which meets every Boolean combination on an infinite set, and also its complement, very importantly, meets the Boolean combination on an infinite set. So how do we do this? Well, we list all possible Boolean combinations associated to this independent family, such that each Boolean combination appear infinitely often. All right, and so at stage n, this is an inductive construction, we will choose two natural numbers in such a way that essentially, so when we have our enumeration, this property here, we'll choose two distinct points which belong to the end Boolean combination in our listing. and it hasn't occurred so far. And what will happen is that this property is going to guarantee that, say, A to n belongs to A intersection Hn. A to n plus 1 belongs to the complement of A intersection the nth Boolean combination. And so clearly, if we just take, say, A to be all the A's with even indices, we obtain an infinite set which enlarges, which is independent over the given countable independent family. All right, so countable independent families are not maximal, and they're classical examples of maximal independent families of size continuum. So this example is due to Fichtenholz and Kantorowicz, and essentially we look at the underlying set is the collection of all finite sets of rational numbers. All right, this is a countable set, and now for each real number we could take the set AR, which consists of all those elements of the set C, with the property that in our set A, below R, there is an even number of rationals. All right, so this, using the fact that the rational are dense in the reals, essentially this gives us that the family of ARs is in fact a maximal independent family. All right. So how does the independence number relate to the other cardinal characteristics? Okay. Now, if we have a maximal independent family, let's look what does it mean that it is maximal. So we take any set which is not in the family. Now, being maximal means that I cannot add it to the family. With other words, I can find a witness to this fact, and my witness is in fact a Boolean combination. With other words, there is a Boolean combination AH, there is some H, or there is a Boolean combination AH, such that one of those two sets, the intersection of X with H, or the intersection of the complement with X with this Boolean combination, is not infinite. With other words, is finite. But this means that, in fact, for each X, we can find a Boolean combination which witnesses the fact that the family of all Boolean combinations associated to our family is unsplit. And so this means that this family, that the reaping number, the minimal size of an unsplit family, is less or equal than the cardinality of our family. So the reaping number is less or equal than the independence number. All right. Now, the second inequality that I want to mention is the fact that the dominating number is less or equal than the independence number. This result is due to Scheller and has an interesting story. Namely, that's the story that Martin Goldstern tells, that in the evening, after a long day of discussion, they suspected that they had the consistency proof of I being strictly smaller than the dominating number. And fresh eyes showed that there is a gap in the proof, and the gap in the proof resulted in this ZFC result. All right, so that's just an anecdote. It is proof. So what is the heart of this argument? That if we have a dominating family, if we have a family of functions from the natural numbers to the natural numbers with the property that every real is eventually dominated by a member of the family, then the cardinality of this set must be less or equal than the independence number. All right. All right, so a little bit more patience. Now we want to compare the independence number to the ultrafilter number. Now, in the Miller perfect tree forcing, there are p-points. The forcing notion adds unbounded reals, so the dominating number is large, and therefore the independence number is large. So consistently, the ultrafilter number is smaller than the independence number. On the other hand, I think that was the result is from 1984. Shellac produced a forcing notion, which is omega-omega bounding, and an iteration, it can be used, it can be associated to a maximal ideal, and the whole construction has the property that the countable support iteration of this forcing notion preserves a very carefully selected maximal independent family, maximum, in the final generic extension. So this proof will play an important role for us today. So in particular, from this construction, will appear this notion of strengthening maximality for maximal independent families that I want to speak today about. So the notion of selective independent families. And in particular, what we can read off from this more complicated construction is a proof that there is a Sachs indestructible maximal independent family, and I want to give an idea of this proof. And as of more recently, we closely related to this original result and yet sufficiently different, we can produce also a maximal independent family. In fact, selective independent will show that selective independent families, so these very special families constructed in this consistency result of Saharan, are in fact preserved also by iterations of Miller partition forcing. All right, so now thinking again about the cardinal characteristics, we come to a little bit of detour comparing the almost disjointness and the ultrafilter number. So in the Cohen model, A is less than U, and on the other hand, it can be shown that also consistently the ultrafilter number is smaller than the almost disjointness number. Okay, so why am I so interested in exactly these cardinal characteristics? Well, one of the reasons is that if you look at the standard cardinal characteristics or the classical cardinal characteristics, the one that have been around for a little bit longer, we have that the almost disjointness number, the independence number, the ultrafilter number are among the characteristics for which we have very little other upper bounds different than the continuum. So there are some exceptions, and as of recently we have a new visitor to this diagram that I will mention very shortly. But this is essentially giving us some interesting information of independence between these natural higher, larger cardinal characteristics. All right, so what can we say about the relation between, so we considered any other pair, and all that we need to consider now is the relation between the almost disjointness number and the independence number. Well, in the Cohen model, there is a Cohen indestructible maximal almost disjoint family. The almost disjointness number is small, the dominating number is large, and so the independence number is large. Well, what about the consistency of the independence number? Smaller than the almost disjointness number. Is this possible? Well, this is a very difficult open problem, which is now known as a problem of Vaughan. And it has been around for a long time, and it is related also to Reuteman's problem. So there are very many difficulties or very many possible approaches that we know that are not going to produce, okay, a good attempt, let's say. However, recently there has been some advancement in this area, namely it's about a year-old result, jointly with Osvaldo Guzman, Cruz Chapital, myself, and Jaroslav Spina. We could show that it is consistent that the independence number is more than a close relative of the almost disjointest number. So AT is, I would write the close relative, a close relative of A. But as any close relative, it is sufficiently different than A. So we'll come back to this result later in the talk, and we'll see, we'll say more about this construction. All right. Okay. So now I want to draw a diagram of all right, so let's see, can I extend my diagram here? No, I'll move on. Okay, so here is a diagram, oops, which is a little bit messy, but includes most of the characteristics that I mentioned so far. Dependence number, here I have to fit the reaping number, the ultrafilter number, and here I have also the, all right, the uniformity of the meager ideal is less trivial than independence number, and then I have some other relatives of the almost disjointness number. Okay, so we know that A and you're independent. All the discussion that I said is very interesting, and we seem to have a comparatively good understanding of this mutual independence. However, very recently, there is a new visitor or a permanent member of this diagram that has been occupying our interest, which is a natural generalization, a cardinal invariant associated to a natural generalization of both maximal of almost disjoint families and independent families, namely ideal independent families. So let me give it a definition. So an ideal independent family is an infinite family B, such that no element of B is a subset of subset mod finite of a finite union, okay, of the union of finitely many other elements of the family. And the minimal, okay, we're interested in maximal such families, which are maximal under inclusion. And such families are called maximal ideal independent families. Okay. And the minimal characteristic is SMM, denoted as SMM. Okay, so what is known about this cardinal characteristic? Well, in a recent work of Jonathan Cancino, Osvaldo Guzman, and Arne Miller, it was shown that in the product of Sachs forcing, it is the case, so it is consistent. So in product Sachs extension, we have that the minimal size of a maximal ideal independent family is equal to F1, is strictly smaller than the continuum. And also it is shown that it is consistent that this characteristic is strictly smaller than the uniformity of the Miller ideal. And so this implies that it is consistently this minimal SMM number is strictly smaller than the independence number. All right, so one of the open questions that is they conclude their work with is asking if if the ultrafilter number and the number SMM are in fact independent, or there is a ZFC relation between them. In particular, they ask what is the value of SMM in the Shelas model of the consistency of I less than U. So, so the new visitor to our diagram is the following very recent theorem of Contino, myself, and Corey Switzer, namely that the ultrafilter number is less or equal this SMM. So in fact, we obtain this new member of our diagram, which I will go back, and it has to be added right here. What we have is this. All right, so what we know is that this close relative to independence and almost disjointness, if you want to think of it in these terms, is in fact independent over. Now we can conclude that SMM and I are independent, since in Shelas model of the consistency of I less than U, by the above result, we have that gives that it is in fact also consistent that I is less than SMM. All right, so that was surprising for all three of us, but it's an exciting development in the area. All right, so now I'm going to go back to independent families and discuss more closely the notion of selective independence and how these selectivities, this strengthening, or these very strongly maximal independent families are forcing indestructible for a few forcing notions. All right, so maximality was essentially saying that given an independent family, whenever we have an intruder, we have a set that we might want to add to the family, we can find a Boolean combination which shows that this is not possible. And showing that this is not possible says that either the intersection of the set with the Boolean combination or the intersection of the complement of the set is finite, with this Boolean combination is finite. All right, dense maximality. Dense maximality is essentially thinking that whenever we have an intruder, not only there is a Boolean combination which would show us that we cannot add this set to the family, but these Boolean combinations are dense. What does this mean? This means that every time I'm given a set and a Boolean combination, I can find the strengthening of this Boolean combination, which is going to witness the fact that I cannot add this set to my family. I cannot enlarge it. So whenever I have a set and a Boolean combination, I can find a stronger Boolean combination such that either AH prime intersection X or AH prime minus X is finite. All right, the notion of a densely maximal independent family has been around for a long time. I think it appeared in the work of Goldstern and Schelach from 1982, when they were looking at the Ripping number and independence number, I think. All right, so moving forward, here is another very useful for us object which is associated to independent families. Namely, given an independent family, irrespectively if it is maximal, densely maximal, we are going to look at the collection of all subsets of omega, or infinite sets of omega, with the property that every Boolean combination can be strengthened to a Boolean combination which is entirely contained into the set. Now, this family is in fact a filter, and we'll be referring to this family as the density filter associated to the independent family. Now, this density filter will capture the combinatorial properties of this filter, will be to a great extent responsible for the forcing indestructibility of certain maximal independent families. All right, so let me remind you some definitions. All right, okay, so a Ramsey filter is not necessarily an ultrafilter, it's a filter which is both a P set and a Q set. So, right, so this should be known. So what is a selective independent family? This is a densely maximal independent family. So all the witnesses to maximality are dense. And moreover, the associated density filter is selective, is combinatorially very robust. All right. Okay, so as I mentioned in the work of Schelach on the consistency of the independence numbers mode and the ultrafilter, that's the first occurrence or the first construction of such selective independent families. They can be obtained under CH. And as we're going to see, they're indestructible by countable support iterations and products of Sachs forcing. So in particular, we obtain the consistency of the independence number being strictly smaller than the continuum. All right, so let me just see something. So I want to give you an idea of how one can construct such family. So let's see. So this is essentially extracted from the consistency of I less than U. All right, so what we have is that we work, of course, under CH. There is a sequence of pairs A alpha for alpha less than omega 1, such that each A alpha is a countable independent family. The set given the pair A alpha, or this pair, has the property that every Boolean combination associated to the countable family has an infinite intersection with the second coordinate that occurs in this listing. So note that A, the second coordinate, A alpha, sorry, is not a candidate to be added to the independent family. But it will, as very soon I'll show, it is a preparation for a generator set of the density filter. So this is the pairs, and now we have that whenever alpha is less than beta is less than omega 1, we have that A beta is a superset of A alpha, and the second coordinate is almost contained in A beta is almost contained in A alpha. So the second coordinates, the first coordinates are increasing chain of independent families, while the second coordinate is certainly a tower. All right, and moreover, reading the paper from 1984, such that, and there is a long list of combinatorial properties indexed A up to J hold, so long list of properties, and eventually these properties will guarantee that the family A star, which is the union of all these approximations, is a selective independent family. All right, moreover, we will have that the density filter is generated by the second coordinates occurring in this construction. So in particular, it can be constructed by, generated by a tower. All right, so this filter, okay, so as you see, so the way that the construction proceeds, it can be, in fact, it can be made quite definable. In fact, revisiting this construction, we were able to show that the consistency, this is another not that old result, it is consistent, no, okay. The consistency of I less than C can be witnessed by a coanalytic maximal independent family of cardinality Aleph1. So this is a result of Brandle, myself, and Yurikomsky, in which what we do is, in fact, we repeat this construction by working over the constructible universe and using the sigma 1 to a order of derivatives. What in addition happens is that, so essentially we construct a sigma 1 to definable maximal independent family, which is selective. What though in addition happens is that the existence of such sigma 1 to definable independent family produces the existence of a coanalytic one. So this procedure that I described here can be in fact made quite definable. All right, but coming from various angles of trying to analyze the construction and certainly thinking about adjacent and related results, we decided to look eventually at just the partial order consisting of all pairs, where the first coordinate is just a countable independent family, the second coordinate is an infinite subset of the natural numbers, which has the property, just as in this construction, it meets every Boolean combination on an infinite set. Now, the collection of all these pairs is, in fact, forms a partial order. The extension relation that one can, a very natural extension relation, it just required that the first coordinate is a larger countable independent family. The second coordinate is almost contained into the first one. And what is interesting is that this partial order to a great extent captures all the combinatorial requirements of the inductive construction, which I described just, namely the generic associated to this forcing notion is going to produce a selective independent family. Now, this forcing notion is countably closed. This is not difficult to see, has the Aleph2 chain condition. And moreover, if we take a generic, then the union of all countable independent families occurring in pairs from the generic form an independent family. The which we're going to see is in fact selective independent, and the collection of all the second coordinates is a p-set. All right, so, all right, I'm going a little bit slow with all these explanations. What we have is that, in fact, the generic object is a selective independent family, and we have all the other related properties. Moreover, what is maybe a crucial point is that the filter, the density filter associated to our generic independent family is generated by the second coordinates appearing in conditions in the generic. All right. Okay, and now I want to go over the proof that this family is in fact Sachs indestructible. Okay. Now, what we are going to see is that, in fact, by already existing preservation theorems, most of our work, is already, something's wrong with my slides. It's already taken care of. Okay, sorry. It's fine. So we have that the density filter is the density filter of the associated family is Ramsey. Moreover, a very important property is not only a p-set, but the fact that this collection of second coordinate is a q-set implies that whenever we have a strictly increasing function, we can find an element of the filter whose enumerating function will grow comparatively faster comparative to this function. So we'll have that at each point n, the value of the function of f at kn is strictly below kn plus 1. And this property will be very important for us, and we'll use it. So we'll play a crucial role in a very carefully designed fusion sequence. All right. Okay, so how are we to show that this family remains maximal in the countable support iteration of Sachs forcing? This would be our next goal. Okay. All right. So let's make the following observation. If we have a countable support iteration of Sachs forcing, then in fact, we'll have that for each alpha, the density filter associated to our family will be in fact generated by the ground model density filter. So essentially by the set FG. So a very short way to say this is that in fact, this property can be read off from a general result regarding quant preservation, from a general forcing result, just by the nature of how these Boolean combinations appear. So this property is essentially has a lot to do with, it's known as quant preserving. Very sorry, I have to switch on my lights. All right.
Vera, can I just ask quickly? By the ground model, you mean this V of G where you have this after the forcing that adds this family, right?
Yes, that's right. Yes. Okay. All right. So so how does this occur? Let me see. Okay. So here is this property of Cohen. When we say that the forcing notion is Cohen preserving, this is again a general theorem of Schellach, which says that if we have a dense open subset, every dense open subset of 2 to the omega in an initial segment of the iteration of sex forcing is in fact contained in a ground model dense open subset of 2 to less than omega. So this is the notion of Cohen preserving. So this has nothing to do, this has very little to do with the Boolean combination. So that's how, let's see a little bit more into this argument. Well, suppose we have our infinite, an arbitrary infinite, or you can think of our generic or the independent family. And suppose we have a set which is forced to be in the filter, the density filter associated with this family. All right, then we can find, in fact, an extension Q, an accountable segment of the independent family, such that in fact Q forces that X dot is a member of the density filter associated to this smaller family, countable family. A is very large. Okay, in the next step, what we can do is we can clearly.
Vera,
yes.
Vera, sorry. Sorry, there's feedback. Could you turn off the mic?
Oh.
Okay. Can you hear me okay?
Yeah.
Okay. So what you said is the theorem of Schla, do you mean it the other way around? Like if you have an open.
Yes, I do.
Right. It's otherwise trivial. Okay. All right.
Yes,
okay.
yes.
Okay.
Sorry.
All right.
Okay, so so if we identify this Boolean, the Boolean combinations with 2 to the less than omega, then we can get a name for a dense open subset of 2 to the omega and apply the above theorem. All right, so I guess this is clear, but if you want, I can give an idea if there's students how this is done. All right, so well, this is straightforward, but so it essentially says that so our condition Q forces that for every H, there exists an extension such that B of H prime is contained in X dot. This is equivalent to Q forcing that X dot is in the density filter. Now we fix H, and we can construct a maximal antichain CH below Q, such that for each R in CH there exists an extension of the given Boolean combination, and R forces that this Boolean combination is contained in X dot. And now clearly identifying FFB with this 2 less than omega, we get a name for a dense subset of 2 to the less than omega. All right, so Cohen preservation. Okay, now what is interesting to point out that in fact this property of being densely maximal in fact corresponds to the following covering property of the power set of omega. Namely, of course, a maximal independent family is, okay, an independent family is densely maximal if and only if the power set of omega can be partitioned as the filter, the density filter of the family, and the downwards closure of all complements of Boolean combinations. And how is this important for us? Well, this is important because of the following general preservation theorem. This theorem is again due to Scherer. If we have a partition, if we have a countable support iteration of omega-omega bounding posets, we have a Ramsey set, in particular, a Ramsey filter, and a set H, which is disjoint from this filter. Now, if for each alpha below delta, we have this partition of the power set of omega, then this property is preserved at limit stages. So applying this to the notion of independent family, this is telling us that in fact, this theorem is taking care of the case of the preservation of the given independent family, of the selective independent family at countable state, at limit stages. So, so if we have a stage alpha, and we know that for each beta less than alpha, A is densely maximal, this means that for each stage beta less than alpha, we have the corresponding covering property of the power set of omega. And so by the preservation theorem, we will know that our independent family would remain densely maximal at limit stages. Aha. And so all that we need to do is in fact apply this preservation theorem of this general preservation theorem to the density filter to generate, knowing that it is generated by this special set and the complements of the Boolean combinations. So our main task, our main work is in fact concentrated from this point on guaranteeing the preservation of selective maximality or dense maximality at successor stages of this construction. All right, so this is the next point that I want to try to go over. So suppose we're at some stage alpha iteration and we know that we have a densely maximal. In fact, we're working with the maximal, the selective independent family that we constructed. All right. Now, suppose that we have that this family is not only densely maximal, in fact, we have that it is selective. And now suppose we have in the generic extension, in VP alpha plus 1, we take an arbitrary infinite subset of omega, which is not in the density filter associated to our selective independent family. All right. Now, by way of contradiction, we'll be very happy if it is contained into a Boolean, the complement of a Boolean combination. So suppose this is not the case. With other words, we have that in VP alpha plus 1, H is not a subset of omega of the complement of any Boolean combination, which means that in fact, the set X has to meet every Boolean combination on an infinite set. All right. And now we fix a condition which forces this property. Okay. So now we have to do a little bit analysis of what our names for reals are. These names for infinite subsets of omega. And we are going to make a very heavy use of the fact that in VP alpha, the family is selective. So we're going to make strong use of the properties of the density filter. Now we have very nice approximations, ground model approximations of our name, namely, to which we refer as outer whole, namely, for each n and every node, n splitting node of the given condition P, we can consider the set of all those natural numbers which are not forbidden by 3P above T to appear in X dot. Okay, so this is a ground model set. And moreover, the condition PT forces that X dot is a subset of this ground model set. So we speak of it as a very nice ground model approximation to what our generic object is going to be. this evaluated mean. All right, so what is interesting is that in fact this outer house, by our hypothesis, are elements of the density filter. And the proof is very short, as you can see. All right, well, if not, then we reach contradiction to our hypothesis that this name met every Boolean combination on infinite set. So all these Boolean, this outer house are in the density filter, but know that there are only countably many such outer house. And now all that we have to do is we have to do a very careful fusion, which would produce, using this outer house, which would produce a member of the filter, an element of the density filter, which is forced to be contained to be a subset of x dot. And this would be a contradiction because this would mean that x dot is forced to be in the density filter. All right, but in order to do this, and know that this construction with some additional requirements, the forcing notion already appears in Shelat's proof of the consistency of phi less than u. The difference is that, of course, the forcing notion there has to take care of additional requirements as the goal, the objective is different. It is to destroy some maximum idea. All right. So how do we do this fusion so carefully? Well, in order to do this, we need a little bit more. We need to pass to some better, stronger conditions, which know a little bit more about the name x dot. Namely, we have to pass to pre-process conditions. So what means pre-process? Well, this just means this condition can be obtained by a standard fusion. We can assume whenever we have the name, the condition P, its X forcing, and the name for an infinite subset of omega, we can, using a standard fusion, we can find a condition, an extension, which has the property that for every node appearing in the n splitting level of P, already evaluates an initial segment of the name. So for every n and every node, there is a binary sequence of length n such that the condition above the node T is already evaluating this is the characteristic function of the name up to the level n as this set. All right. So we say that P is preprocessed for x dot. All right, so how is this going to be helpful for us? Well, the outer house associated to preprocess conditions are particularly nice. Now, if P is preprocessed, then in fact, the outer house contains a lot of information already about the name. In particular, we have that the outer hull consists of all those natural numbers. So this, by definition, these were the numbers that are not excluded by the condition, by the tree above the node T. But what we obtain if we assume that P is preprocessed or passing to a preprocessed extension is that in fact a natural number M appears in the outer hull if already for some node RT which is comparable with T, the condition P above RT forces that M is in X dot. So this is the condition. And moreover, we will be able to find these witnesses of a controlled length. If we don't preprocess the condition, we might need to jump very high in order to get a witness for a natural number M. But if we first preprocess, then in fact, we will have that such witnesses of minimal length already for a given natural number m, which is in the outer hull, such witnesses will already appear in the m plus first splitting level of P, provided that the condition is preprocessed. Okay, so far we just work with names and the Sachs forcing, the partial order. We did not use very much the properties of the density filter, apart from the fact that we know that the outer hulls are members of this density filter. Okay. Now, okay, so here I wanted to give you a proof of this fact, but I think that I'm just going to move on. All right. So since we know this density filter is a p-set, we can find a pseudo intersection of all the outer hulls, which is from the density filter. The outer hulls are, after all, only countably many because P is a countable set of nodes. It's a tree. All right. Now, so we use the P property. Now, moreover, since P alpha is omega omega bounding, we'll be able to find the ground model function which would measure how far we have to go on to find the next member. So we'll find a ground model function which we can assume to be strictly increasing with the property that all members of the set C0 with the pseudo intersection, which are above f of n, are already in all are elements of the intersection of all outer hulls appearing to some initial up to stage n, associated to nodes below n of splitting height less or equal n. Okay, this can be done. We're not using not very much. Okay, and now comes a little bit more. Now, if you try to use all of this information so far in order to guess a member from the density filter to force that the member of the density filter is contained into the name X, you very quickly realize that you need a little bit finer control. And this finer control will come from the fact that the density filter is in fact also a Q set. All right, more precisely, since we have that the density filter is a Q set, we can find, and we have the function f, which was measuring how fast our approximations grow, we can find an element in the density filter whose enumerating function will have the property that f, we can essentially are required to grow as fast as we want. We can in particular have that f of jn plus 1 plus 2, f of jn plus 2 is strictly below to jn plus 1, where jn is the enumeration, increasing enumeration of this, this element of the filter. Okay, so what is this producing? This is producing an element of the filter, of the density filter, which has, which is this very precise, for which we have a very precise growth. We have that the n plus first element of this set C from the density filter is in fact contained in all outer hulls associated to nodes of splitting height less or equal kn plus 2. And this is a technical requirement because our goal would be to construct a fusion below T using these outer hulls and using this very carefully chosen element of the density filter, which would force that, which would guarantee that the set C itself is contained in X dot. So we have it locally, but now we have to glue all this information for the entire set. Otherwise, the whole procedure is not bringing very much. Okay, and now after we set up the stage, after worked so hard to guarantee that the set is preprocessed, to guarantee that we have this very carefully designed set from the density filter, we can in fact construct a fusion sequence which has the property that the end member of the fusion sequence guarantees that the end element of the set C from the density filter is forced to be in the name X dot. And so in particular, the fusion of the whole sequence will guarantee that the set C dot is contained in X, is a subset of X dot. With other words, the fusion will force that X dot is an element of the density filter, which is a contradiction to our initial hypothesis. All right, so this is this fusion argument, which in fact can be read off from the proof of the consistency of phi less than mu. Okay, so we know that the independence number can be smaller than the continuum. And for a long time, there has been, at least at the time when I started looking at this at the spectrum of independence, there seemed to be bounded information as to what the possible sizes of maximum independent family is. However, before, so chronologically, the results that I'm presenting, they're not chronologically, don't correspond to how they actually developed and appeared. However, since technically what I'm going to present now is closer to what I just said. Anyway, what I want to say is that before moving into discussing the spectrum of maximum independent families, I want to look at some recent advances in this, which can be seen as advances in Vaughan's question if consistently the independence number is smaller than the almost disjointness number. So in particular, what we were able to show is that it is consistent that the independence number is smaller than this number AT, where AT is defined as the minimal cardinality of a maximal almost disjoint families of subtrees of 2 to the less than number. And the proof that we were able to find was to a certain extent inspired by the Sachs preservation of selective independent families. However, there were some very serious obstacles we needed to overcome, and the most difficult part of it was working in a good way with the fusion. But let me tell you a little bit more about what AT is and what was known about it and how we came up to this result. All right, so 1980, a paper by Arne Miller. If X is an uncountable Polish space, then AT is in fact the minimal size of an uncountable partition of X into closed sets. In fact, the partial order which would play a crucial role for our consistency of I less than AT appears in this paper, and we refer to it as Miller partition forcing. So what was obtained in 1980, in fact, using this forcing notion, it was shown that consistently the covering of the meager ideal is strictly smaller than this minimal size of an uncountable partition of 2 to the omega. With other words, the forcing notion that appeared, one of its first purposes or effect results of application is that it adds a generic which eliminates a given uncountable partition of X into closed sets. All right, so this forcing notion. So what else we know about AT? AT is small in the Sachs model. The dominating number is less or equal AT. So even though we want to think of AT as a close relative of the almost disjointness number, we should be careful because remember that D and A are in fact independent. Well, okay, so it is consistent that 8 is alpha 1 and the cofinality of n is of the no ideal is omega 1. So how was this obtained? That was a few more steps. Okay, so this forcing notion is in fact omega-omega bounding. It has the Lever property, so it has the Sachs property. Okay, so what we were able to show and how we were able to extend these results is by showing that in fact, in the iterated Miller partition forcing, the majority of the cardinal characteristics for which we think as characteristics that do not have other classical upper bounds apart from the continuum are all equal to alpha 1. So we have the almost disjointness number, the ultrafilter number, the independence number. They are all small in the Miller partition model, while the AT number is large. So the fact that the almost disjointness number is small is due to Krushak, Guzman, and there is one more author. So they essentially show that Miller partition forcing preserves tight, almost disjoint families. What we were able to show is that it preserves p-points and selective independent families. Okay. All right. So what is this forcing notion? Well, this forcing notion consists of perfect trees. However, the notion of a fusion is very special. So let's see what is this forcing notion. Given a partition of 2 to the omega into uncountable closed sets, the partial order associated to this partition is the set of all perfect trees which have the property that each of the set C alpha is nowhere dense in the set of branches passing through this tree P. And the order, the extension relation is just inclusion. Now recall that if we have a set A, the set A is nowhere dense if for every node in the tree we can find an extension, a stronger node in the tree with the property that all branches passing through this extension avoid the given set A. Okay. So what are the properties of this partial order? Well, it is proper. In fact, it has axiom A. It has the Lever property. And if we take in a generic extension, then the given partition with which we started is no longer a partition of 2 to the omega. 97, Ottmar-Spinas showed that the forcing notion is in fact omega-omega bounding, and so we obtained that it has the Sachs property. Okay. So here is the result by Grossman, Hoschak, and Telech that iteration, so this forcing notion strongly preserves tightness of tight maximal almost disjoint families, and in fact, a tight maximal almost disjoint family would survive the iteration of such forcing notions, which leads to the consistency of A smaller than AT. So this is the result which they obtain. Is consistent that A is strictly smaller than AT. Okay. So why is this fusion? What is the notion of a fusion? Now, on one side, this is a forcing notion of perfect trees. So it is similar to Sachs forcing. On the other hand, when you look at the forcing and how the fusion arguments work in this forcing, it very much reminds fusion typical for rational perfect tree forcing. Okay, so what exactly am I talking about? So suppose we have two conditions in the partial order in the partition forcing associated to some family C. Then we say that P is n below Q if and only if P is an extension of Q up to the n splitting level, the two conditions coincide, and now things start becoming very interesting. For every node which appears in the n splitting level, the leftmost branch which passes through T in the weaker condition Q has to be a branch of the stronger condition. So however am I to thin out, I'm not allowed to throw out this leftmost branch. And remember that if I'm aiming now to have a very fine fusion argument with which I can pick and choose what to keep and how to thin out the condition, this is a huge risk, a huge difficulty, because I'm prevented to whatever I do if I want to have a fusion, I'm prevented of touching this leftmost branch. Okay, and moreover, for each T which appears in the n splitting node, if it happens that this the leftmost branch passing through T in the weaker condition is an element of the alpha member of the partition, then there is an extension in the stronger condition, which is n plus 1 splitting, and any branch which passes through this stronger condition S, stronger node S, and belongs to the stronger condition avoids the partition, the set C alpha. So on one side, I have to, if this is the leftmost branch, I have to keep X QT, and I have to have this splitting away from the leftmost branch. So this, superficially, at least to me, this very much reminds me of Miller rational perfect tree forcing arguments. Okay, so if you have, that's the definition from 1981, if you have a fusion sequence, then the fusion is in fact a condition. Okay. So in order to work with this forcing notion, we had to make some advances in understanding how fusion in this partial order works. So we say that this X and Y, which are functions from omega into 2, are C different if they belong to the different elements of this partition. Okay. And we say that the 3P is C branching if for any node in the tree, there are C different branches extending this node. Now the following are equivalent. If we have a tree, then this tree is in fact a condition in Miller partition forcing, if and only if P is C branching, if and only if P is a perfect tree, and the set of all nodes passing through all branches of the tree contains a countable dense subset with C different branches. All right, so we are very close to stating our notion, the notion of fusion on which we eventually had to work with. But before that, we come with the following notion. So we say that the set X is a P witness for the nth level if this is a set of branches through the tree. It consists of C different elements, and each node appearing in the end splitting level of the tree of 3P is in fact an initial segment of an element of our set, of our chosen set of C different, yes, an element X of X. Okay. Now, if X is a p-witness for the n plus first level, then note that each node from the nth level is contained in two C different branches. This is already included into the definition. Okay, so what is our notion of fusion? We introduce the notion of fusion with the witnesses with the sole purpose is that we can thin out our conditions by not promising to keep the leftmost branch, but by promising to respect some very carefully chosen substitute of this leftmost branch. So here what it is, we have that Px is n below Qy. This is our notion of fusion with witnesses. If P and Q are conditions in Miller partition forcing, P is an extension of Q. X is a superset of Y. X is a P witness for the n plus first level. Y is a Q witness for the nth level. And with the machinery that we introduced, in fact, we can guarantee that we do the fusion of such a sequence with witnesses is in fact a condition in the partial order. Now, these witnesses would allow us, though, to have a much finer control of thinning out and, in a certain sense, gluing back together trees to a condition. Okay, so one of the results that we had is this forcing notion preserves split points. The argument is similar. We do use the notion of fusion with witnesses. On the other hand, there is certain similarities between our proof and the proof that Miller rational perfect tree forcing preserves split points. All right, so the notion of selective independence or indestructibility of maximal independent families has already been around for a while. Then we have Shelas paper, then 2019, we looked at free sequences, and very recently this notion reappeared in terms of some definable properties study jointly with Corey and Jeffrey Bergfalk. All right, so this notion of selective independence, in fact, is comparatively well understood. All right, so now going back to the whole machinery of how we preserve, how we show that the selective independent family is preserved in the countable support iteration of a Sachs forcing. What we did is, in fact, we used general preservation theorems, which allowed us to essentially reduce our task to showing that Sachs forcing itself preserves selective independent families. So what we are going to do here, these general theorems, in fact, show us that all that we need to do is we need to show that Miller partition forcing preserves selective independent families itself. And this thanks to this general preservation theorem, this would result in the consistency of the independence number being alpha1, while we can use an iteration of such partition forcings going over all possible partitions to guarantee that the AT number is large. All right, and well, from a bird's eye, from looking from far apart, the proof looks horribly familiar to what we just saw for Sachs forcing. We start with a selective independent family, and we know that we just have to show that the family remains maximal after we force with Miller partition forcing. So we take an element which is not in the density filter of the family, and suppose by way of contradiction that this family is not contained in the complement of any Boolean combination. Aha, but this means that we can find a condition P, a name for our counterexample to maximality, so that for every Boolean combination AH, our condition P forces that our name meets every Boolean combination on an infinite set. Okay. All right. Well, with our notion of a fusion, in fact, one can again using one can produce preprocessedness. One can require that initial segments of our perfect trees have sufficiently good information about the evaluation of the name, an initial segment of the name yt. Of course, here I mean the characteristic function of the set y, of y dot. And then again, we can speak about outer house, which are again for every element of the tree, T, every node of the tree, just the collection of all sets, all natural numbers M, which are not forbidden by the condition, by the tree P above the node T. Okay, one can show that, in fact, again, this is an outer house. This is a ground model approximation to the name that we are, in fact, trying to obtain some further information about. All of these outer hosts are in the density filter. And moreover, if the condition is preprocessed, we can have that a natural number M occurs in the outer host associated to a splitting node, end splitting node, then we know that in fact already an initial for some T in the M, for some M, for this very same M, there is a node T in the M splitting node of the tree P, which extends S, which already forces that M is in Y dot. So again, this is an interplay between the properties of the outer hull and being preprocessed. Okay, but now we have set up our stage very, very carefully. And using the fact that the density filter is both a P set and a Q set, in other words, Ramsey, and using this extra flexibility of not committing to the leftmost branch, but having our side conditions, our witnesses to construct a fusion sequence, we can construct a fusion sequence, and we can find an element of the density filter, C, which is forced to be contained, to be a subset of the name Y dot. So essentially, you can think of every time we thin out in a very special way to guarantee that the next member of C dot from the enumerating function of the name of C check is forced to be in Y dot. And so the Qn forces that, or Qn plus 1 forces that n is in, okay, the nth element of C dot, of C check is in Y dot. And so the fusion would provide that the whole set is a subset of Y dot. And this is the contradiction. All right, I guess I'm running out of time. So that would be it for today. And if you have patience, we'll move on to the spectrum of independence next time. All right, thank you.
Okay, are there any questions? Anybody?
I have a possibly so these density filters. How
Yes.
big are they? How close can they get to ultrafilters, for example?
They're never ultrafilters.
Okay, so then the question remains: how close can they be?
Okay.
Can they be? For instance, can they have only a few ultrafilter extensions? Probably not. Do they?
Yes. So if the family is densely maximal,
Mhm.
the density filter, in fact, has the following interesting property. So where did I? Aha. I'm sorry. I have to share again. Okay, so if the density filter, no, you're not seeing anything. Oh, sorry, yes. Okay, so if the family is densely maximal, okay, so this is, okay, so if A is densely maximal, then this density filter is in fact, is the unique diagonalization filter associated to the family A, where this is a maximal filter, a filter which has property that every member of the filter meets every Boolean combination on infinite set.
Mhm.
And is maximal with respect to this property. So given an arbitrary independent family, we can define a filter, just a filter. We can look at all filters which have the property that their members meet, their elements meet every Boolean combination on infinite set. And now we can take a filter which is maximal with respect to this property. Such a filter has very nice, is useful because Matthias forcing with respect to such filter adds a real which extends the given independent family
Mhm.
in a very good way. So if the density filter is in fact such a diagonalization filter, provided that the family is densely maximal. So at least partially, I hope this answers.
Thank you.
Any further questions? So it looks like we're all satisfied. Thanks again for the talk. Very nice.
There.
Oh, that it was all right. Okay.
And starting next week, we want to begin 15 minutes earlier at 12:15. I mean, Vika is going to send out another reminder, I guess, next week, but just so
Yep,
that you're
will do.
already prepared.
That works good for me. Friday, late afternoon. All right, thank you so much for having me. And
All right, thank you. All right.
Next week there. Bye, everyone.